Okay, so logarithms, again, the way they work is basically they tell us about an exponent, right, or a power that we, don't know or are looking for or something like that. But that means when you write a logarithm, like when I write, here I said 5 squared is 25, and that's equivalent to the log base 5 of 25 being 2. But when I write this, like what this whole thing is a power. It's an exponent, right? It's telling me how many of these I need to get here, right? So the fact that the answer here is 2 is, again, telling me about a power on the number 5. It's giving me an exponent. So when the base matches, all that we're doing is measuring this number in terms of steps of multiplying by that base. So this log is 2 because 25 is 5 times 5, right? It's 2 copies of 5 multiplied together. So what's the natural log of e to the 9th? That means the same thing as the log base e of e to the 9th. So what this is asking is how many e's are in e to the 9th? How many e's is 9 copies of e? 9, right? The bases match, they're inverses, they cancel, they undo each other, however you want to say that. Just in case we need the reminder, log with no base written means base 10, or the common logarithm, because we do everything base 10, right? ln means base e or natural logarithm. And those are the two that, any calculator that knows how to do a log at all knows those two, right? You probably have a dedicated button for those two. They probably share a button with 10 raised to a power and e raised to a power because they're inverses, or sort of two faces of the same idea. So that's how log works. Okay. Today we're going to look at some properties for dealing with logs that come out of exponent rules. So let's just start with that, some properties of exponents. How do you simplify something like 3 squared times 3 to the 5th, where you multiply like bases? You add. Why do you add them? That is how you do it. You add them. It's 3 to the 2 plus 5. And 2 plus 5 is 7. Why is adding what we do, though? Okay. Okay, so on one hand, because it gives the right answer. Yes, sure. What does 3 squared mean? 3 times 3. What does 3 to the 5th mean? Yes. Same idea, but 5 of them instead of 2, right? So how many 3s do I have sitting there then? 7, right? 1, 2 plus 5, 7. So these exponents, like whole number exponents like that, are just shorthand for multiply a bunch of these together, right? But nobody wants to write out 3 times 3 times 3 times 3 times 3. So we just write 3 to the 5th instead. This is shorthand for multiplication. That means when we multiply, all we're doing is totaling some more up, right? It's this many and then also some more. So we add them together to get 7. How does division work then? Subtract, because you're doing the same thing, only kind of in reverse, right? So 3 to the 5th means 3 times 3 times 3 divided by 7 copies. 5. Not 3, 5. 3 of them on top, 7 on the bottom. So what happens is that you can cancel then 3 of them, and you're left with 4 in the denominator, which I can also get to by doing 3 minus 7, which is -4, which means the same thing as 1 over 5 to the 4th. right? So I would cancel, there are more in the denominator, which means that's where they end up, right? Whatever the, whatever's left over, whatever the overhang is. 4 copies of those, they'd be left in the denominator, and then, just a 1 on top to kind of hold the place, right? Okay, you subtract them, top minus bottom. What about a power then raised to another power? Multiply. Why do we multiply?
3, 4 times.
This is 3, 4 times. So it's 3 and then 3 and then another 3 and then another 3, right? Which I can do is 3 plus 3 plus 3 plus 3, or I could use the shorthand for adding a bunch, which is multiplying. So we multiply 3 times 4. Or 12. Because really, this is just like a shorthand or a more compact way of writing a bunch of things like this. And multiplication is just a more compact way of writing a bunch of additions when we're dealing with whole numbers, right? Okay, so that's how exponent rules work, right? That's how we combine powers on like bases when we're dealing with exponents. What we're going to look at now is how that kind of translates to dealing with logs. So notice that things that are across from each other look pretty similar. How would we find the log base 3 of 3 squared times 3 to the 5th? First of all, what does the log base 3, ask, or what's it looking for? How many 3s? What power of 3? Like what, it's base 3. So this is asking basically how many 3s are in here. Okay, well, how many? 2 and then 5 more, so 7 total. Now I could do that a couple of different ways. I could just simplify the stuff inside like we just did, right? 2 plus 5, so 3 to the 7th. So the log base 3 of 3 to the 7th. How many 3s are in 3 to the 7th? 7 of them. Another way I can look at that, though, is that in some sense, what I'm doing is saying, okay, how many 3s are right there? Ignore the part that I scribbled out. Just look at the first part. How many 3s are in 3 squared? Now, how many 3s are in 3 to the 5th? 5. And how many total is 2 and 5? 7. So another way to look at this would be to say, okay, well, I can just do these one at a time if for some reason that would be more manageable. That's 2 plus 5, which is 7. Because again, what the log is doing is giving me an exponent or finding a power, right? What power is this? Well, okay, it's 2. Log base 3 of 3 squared would be 2. This one would be 5. And we add them together because multiplication, the way you combine is by adding the powers, and that's what the logs are, right? That's why it becomes addition. The cool thing about this, well, anything about this, cool is subjective maybe, but is that this works even when the bases aren't exactly the same. So you can always do this. You can always use this idea of splitting up multiplication. So if I had, say, the log of, or log base 3 again, of 3x maybe, 3 times x here, I can split that up in the same way, even though it's not all going to clean up quite as nicely. This multiplication, I can still divide up into the sum of those separate pieces. Now, one of those cleans up. The log base 3 of 3 is 1. X is just X here. I don't have any kind of context or anything for what it means. So I can't really do anything with that, but I can split those up We can use this in solving, we can use it in thinking about domain. It gives us another perspective on thinking about the functions and maybe how transformations work and that kind of thing. This tells me that a horizontal like stretching thing for a logarithm, I could also think about as shifting it up instead, right? So there's, some other stuff that I can kind of get out of this that helps me to, deal with the functions. Okay, so that's called the product rule for logs. The log of a product turns into the sum, you can't read that. The sum of the separate logs. Okay, so what do you think happens with division then? Comes subtraction. So this I could do, directly, of course, because I just did it. Right, we know what the thing on the inside simplifies to, or that's also the same thing as the log of the top minus the log of the bottom. That's the quotient rule. So logs are really good at dealing with multiplication or division because I can break them into simpler pieces by just splitting them up and turning it into addition or subtraction, which are, just easier operations to do, right? So products, quotients, I can break those up. What about a power? I mean, we can do this one directly, right? I can just look at this and write down the answer. What is the log base 2 of 2 to the 12th? 12. Because what the log base 2 asks is, hey, how many 2's are in here? 12. Okay. Again, though, another way to think about this, and we did this a little bit last week when we talked about equations. I did stuff like this and said, hey, if I, forget that 12's even there. How many 2's are in 2? Right? Log base 2 of 2 is 1. Okay, this 12 means there are 12 copies of that sitting there though, right? So 1 12 times gets me 12. What we're doing, or a way that you can write down what we're doing there, is saying, okay, this 12, it really just means 2 times 2 times 2 times 2, 12 times. So if I think of that as a product, I could split them up and add, and I would get 1 plus 1 plus 1 plus 1, 12 times. But a more compact way to do that is that I could take that exponent and bring it down and treat it like it's a coefficient. Treat it like it's a number of copies, right? So that's 12 times 1, which is 12. That's the power rule for logs. This is just a shorthand for that. And this multiplication is just a shorthand for adding a bunch of times. So logs are good at multiplication and division, and powers are really just a kind of multiplication. So logs are really good for breaking these things up. What we're going to need to be able to do with these, the next couple of days, we'll get into solving equations, and we'll see how this can come into play there, and maybe make life easier on some stuff. You could also use this for things like domain or thinking about graph transformations and sometimes get a little different perspective there. There are some other like historical reasons that we don't care about so much anymore because we have calculators. But what we're going to do for right now is just practice like using the rules, right? Using these properties to deal with things. So flip over to the back real quick and take a look. What we're going to do for today is work on taking either a complicated thing, the log base 3 of big jumbled mess of stuff, and splitting it up, using these rules to break it up into several smaller, easier to deal with pieces. I'm going to call that expanding. So take this logarithm and expand it into several. So like my final answer here is going to be, maybe 2 or 3 pieces that are added and subtracted together, but each one is in, simpler terms to deal with. Or go the other direction. So take something like this and combine, right? Which the way our book describes combining is condensing. So we're going to talk about, condensing, combining these things. My answer here then would be a single log of, something. Okay, so to get started, here are a couple where I've, kind of framed things out for you a little bit. So take a minute and think through how you would expand these, right? So start here, figure out what rules or properties you can use to break things up to put it into simpler pieces.
There was something, Magnolia vacation.
Yeah. We kind of had to go with something closer to home, but for that one. Okay, no, but it was like 20 minutes between things. The log of 2x. What's going on? I don't know how I did that. It's a fun little triangle though. What's going on there that we can reduce, simplify, expand, deal with? It's a product, right? It's multiplication. That means when I split them up, I split it into two separate logarithms, but we add those together. So sort of the cost for doing it is that I have more pieces to deal with, but the thing I get is that the pieces are simpler. We know we're done here when I can't take things down any further. So does the log, which means log base 10 of 2, clean up nicely? Like, does that one come out to be, 1 or 5 or something nice? Is that one I can do in my head? No, because 2 is not a power of 10 that I recognize, right? So if it was the log of 10 or the log of 100 or the log of 1,000 or something like that, then I'd say, okay, well, that's 2 or that's 3 or whatever. Log of 2, that one's a mess. I'm gonna leave it like it is. Plus the log of x. I don't have any like context for what x is. So for right now, x is just a parameter, just leave it like it is. But that's as simple as I can make that. That's as much as I can break it down. The log base 3 of 5x over 4. What can we do there? The log of 5 plus the log of x minus the log of 4, right? Dividing by 4, that term becomes negative then when I split it out. In the top, I've got 5 times x, so we add there. And then again, neither of these, numerical logs clean up nicely, so I'm going to leave them like they are. And then the x is just an x. Okay. How about this last one? Let's do this in kind of 2 stages. It's the log base 2 of a half times x cubed. So first the multiplication. This would be the log of a half plus the log of x cubed, right? Okay. Then one at a time, can I do anything else with this? Can I take the log base 2 of a half and get something like get an exact value? Yeah. What is it? What power of 2 is 1/2? Or how do I write 1/2 as a power of 2? -1. It's the reciprocal, so negative, of 2. So 2 to the first. Or again, you type it into your calculator and find out that it's -1, right? That's fine too. Plus the log base 2 of x cubed. Can I do anything else with this? X doesn't really mean anything, but x cubed has a power on it. We can always deal with exponents with powers inside a log by bringing them down. All right, so that's that power rule. This is asking how many 2's are in x cubed. Well, I don't know, but whatever it is, it's going to be 3 times the number that are in x itself. So 3 times the log of x. Circle this. So here to here, we've got a product rule happening. And then here there's a power also. Okay. So logs, no, I'm recording this one, so I should do it on the screen. Logs are really good at dealing with multiplication, division, or powers using, these product and quotient and power rules that we just talked about. Logs are not good. Some would say bad even. At dealing with addition or subtraction. Addition or subtraction on the inside of a log in the argument of a logarithm. Think about what that means graphically. If you're adding or subtracting, 1 or 5 or something like that, that's a shift to the right or left. That changes the domain. That moves that vertical asymptote around. That means that we can't do some of the stuff that we would normally do with other things with logarithms in the same way. For example, you cannot distribute a log. If you have the log of x plus y somewhere, or the log of x plus 1, or the log of 1 plus y, or whatever, with addition on the inside, we're just kind of stuck with it. I have to treat these things like they're glued together, basically. I can't break that log up at all. I definitely can't write it as the log of x plus the log of y. That's not how they work. Logs measure exponents. Because they measure exponents, stuff like this does not simplify nicely in any kind of way. That's what I mean when I say the logs are bad at addition or subtraction. I can't split that up at all. I'm just stuck with it. So if I look at a problem, like flip over to the back and look at some of the stuff that's there, a couple toward the bottom, there are places where you have an x plus y in there, or some kind of addition that's kind of already there. That's going to be there in your final answer too, then, right? Because there's not going to be anything we can do to simplify or get rid of that. Okay, does anybody have any questions about anything at the moment? All right, so there's a bunch of stuff on the back there. What I want us to do, start this again, okay. All right, let's talk about a couple of these real quick. Let's do 6, maybe. All right, 6, there's a bunch of stuff going on. Kind of the biggest thing there, though, right? The thing that sort of connects everything together. If I was going to describe this to somebody, I'd probably start by saying, the stuff on the inside, start by saying it's a fraction, right? So the biggest thing happening is that division then. So how would I deal with that? Stuff on top minus stuff in the bottom, right? Okay, so the log of the top minus the log of the bottom. Then, zoom in mentally and just look at this piece and do what else we can do here. And look at this piece and do what else we can do there, right? So what else can we do here? Well, it's x to the 5th. Times y cubed, right? So if you've got a multiplication on the inside of a log, you split those up and that becomes addition. So it's the log of x to the 5th plus the log of y cubed. The base part, if we're talking about x and y and the base is 3, it doesn't really matter, right? Because I don't know what x is, I don't know what y is. They don't really mean anything here. We're just using them as symbols. So I have a reason to use these properties to split things up. So I don't really care what the base is here. It was 3 to begin with. It's going to stay 3, but I'm not really doing anything with it. Here, though, minus the log base 3 of 9, a numerical thing like that, then I do care. Is 9 a nice power of 3? Yeah. So that log reduces down to 2. Okay. Now, can I do anything else here? the log base 3 of x. Again, those things don't have anything in common. I'm going to be stuck with the x at some point, but it's x to the 5th. So what else can we do?
5 log.
Yeah. Bring that 5 down. It's 5 times the log of x with, base 3 still. Power rule though. Bring those down. Plus 3 times the log of y minus 2. Now again, without knowing anything about what x or y are, that's as far as we can take that. But there's no multiplication, there's no division, there's no exponents left inside the arguments of these logarithms. Okay? Okay. 9 maybe? Big grouping symbol here, which means that these both get this coefficient 2, right? I would distribute that 2 through. So 2 times the log base b of k. That's the log of k squared. And 2 times the log of m would be the log of m squared minus the log of a. Okay, so we got all of the sort of coefficients cleaned up, right? So I've got log, no coefficients, no stuff hanging out outside. Now I'm going to start combining. And how are we going to combine these? Yeah, we've got subtraction here. That's going to turn into division. So we've got k squared. I'm going to have one big logarithm. We're going to be dividing. What needs to go on the top? K squared, because that term's positive. What needs to go on the bottom? M squared and a. So we're taking k squared, we're dividing by m squared, and we're also dividing by a. Now, if you wanted to do that in like stages, you could do k squared over m squared all over a, but that's the same thing as this, right? Just fraction arithmetic that does the same thing as this does. So terms that are positive are going to end up being in the top. Terms that are negative are going to end up being in the bottom. Real quick, let's talk about 10. Biggest thing going on there is, again, the division. So start with that. Then look at the individual pieces more closely, right? So forget about this for right now. Let's just look at this first one. What else can I do there? There's a square root, and a square root's the same thing as a 1/2 power. And a power I can bring out. Now the x plus y part I'm stuck with, because logs don't know how to deal with addition, subtraction, because that's not how logs work. They're exponents. They're a multiplicative thing. Addition or subtraction we're stuck with, then that's as good as that's going to get. The other piece, it's the log of 16 times x. So that's the log of 16 plus the log of x. But be careful when we do that, because what we just did is take one thing and split it into two things. And when you take one thing and split it into two things, you got to treat those two things like they came from the one thing, because they did, right? So subtracting, but subtracting this quantity, which means distributing. Can we clean the log base 4 of 16 up, the numeric part? Sure, 16 is 4 to the second. But those are both negative, and again, it's for kind of the same reason they were both in the denominator to begin with, right? We were dividing by both of them. They should both end up being negative. 11 is very similar. All right, y'all hang on to those. Finish up whatever you haven't finished up. Notes are in Blackboard. You should be good to go for the 6.3 homework now. We've talked about everything there. So get into that and see